All right, so let's get started. In today's class, we're going to consider the naive Bayes classifier. All right, and we will first see the intuition behind naive Bayes classifier when we go to the whiteboard. Then after that, we'll go to the lab session and then see how we're going to actually build our naive Bayes classifier. Okay, so naive Bayes actually rely on what is called the Bayes theorem, right? Naive Bayes relies on what is called the Bayes theorem. Okay. And the Bayes theorem is nothing but the advanced form of the conditional probability. All right, that is how do we modify our existing probability given a new information. All right, so if we take for instance maybe you want to, let's say you have a meeting. Let's say you have a meeting at a different city, right? So if we take for instance India, for instance, and if you're living in a city like Bangalore, right? If you're living in say Bangalore, and then you have a meeting at say Delhi, right, in the next day. If I ask you what is the probability that you go to Delhi for the meeting at the next in the next morning, right? And the meeting is quite crucial, so it's important to you. And if I ask you what is the probability that you go for the meeting in the next day, right? Maybe you might end up saying that the probability that you might go to for the meeting the next morning will be somewhere around 0.8, right? So there is a high probability because the meeting is more important to you. Okay. Now, what if I give you another information, right? What if I give you an additional information that considering the report from the weather forecast, tomorrow there's actually going to be a heavy rain, right? There's going to be a very heavy rain with some thunderstorms, and there will be no transportation. The transportation service is not going to move. There will be no airplanes, right, going. So it's actually going to be difficult for you to transport yourself from say Bangalore to Delhi, right? So if I give you such information, then I ask you again, what is the probability that you are going to go for the meeting the next morning? Maybe now at this time you might say maybe 0.4, maybe something like that. Okay. So now you have your original probability, right? So this one was your original probability, right? This was your original probability because initially we are having a high confidence that you go for the meeting tomorrow, right? Because the meeting is more important to you. Okay. And then having given you an extra information that there's going to be heavy rain, right? There's going to be heavy rain with some thunderstorms, and there will be no transportation, and even the airlines are not going to operate, right? Now, if I give you that information, you tend to modify your probability, right? So now you tend to modify your probability to a new probability. Now you have reduced your probability. Okay, so in this case, you can see that initially we're having this given a certain condition. Now you're having this probability. So basically, that is what the Bayes theorem is about: modifying your existing probability, giving new information. Okay, and it's not always going to be reducing the probability. It could be increasing the probability. Okay, maybe you need to, maybe if you take the lockdown for instance, right? If you go for groceries at the end of every month, and then the government say that the next morning there will be a lockdown, meaning that if as a normal circumstance it is not at the end of the month, you are not going for groceries, isn't it? So maybe in the middle of the month you got that information, right? You got that information that there's going to be a lockdown the next day. So you go for groceries even if it's not at the end of the month, right? Just to save yourself, right? And initially, if you had not gotten that information that there's going to be a lockdown and it's in the middle of the month, maybe if I ask you what is the probability that you might go for groceries in the next morning, maybe you say 0.2 because at the normal circumstance, you don't actually go for groceries. At the middle of the month, right? Maybe that is what you do. You only go for groceries at the end of the month. So if I ask you in the middle of the month that what is the probability that you go for groceries, right? You might say that's 0.2 because you are not even willing to go for it. But if I give you a condition that there's going to be a lockdown rules, starting from the next morning, right? There's going to be lockdown. So in that case, you might want to adjust. Your probability, because now there's going to be lockdown. So you will need the glossaries, whether it's time for it or not, right? Whether it's at the end of the month or in the middle of the month. So maybe you might increase your probability to go for glossary the next. I mean, maybe in that particular evening, right? Maybe you might increase it to maybe 0.7, right? Maybe something like that, 0.7. Okay, so given the new information, right? Given the new information, you might want to adjust your probability with regards to the new information. Okay, and that's what the naive Bayes is about. That's what the Bayes theorem is basically about. Okay, so how do we modify our current probability given the new information? That's what the naive Bayes will actually help us to do. Okay, it is actually a supervised machine learning algorithm, and it's mostly used for classification problems, right? For instance, if you want to make a prediction whether to travel or not, or whether to grant a customer loan or not, right? Or whether to grant an employee access to a resource or not. So basically, answering the question of yes or no, right? Bayes theorem is actually going to help you, and whether to actually classify an email as spam or not spam, right? Bayes theorem is actually going to help you to do that. Okay. So now let's see this particular example over here. Okay. So let's say we have this. So we consider this example when we are dealing with the logistic regression, right? So in the logistic regression, we consider the same Pima Indian diabetes data set where we try to predict whether a patient will have diabetes or not, right? Whether a patient is diabetic or not diabetic. Okay, so we use this during the logistic regression class, and we're going to use the same thing. So if we base on the, or if we are using the Bayes theorem now, can we predict, right, based on the information that we have here, right, based on these information that we have, right, can we predict whether a patient will have diabetes or not, right, whether the person will have diabetes or not diabetes? Can we do that? Okay. All right, so now before we use the Bayes theorem to actually build a model to predict whether a patient will have diabetes or not, right, or whether a patient is diabetic or not, let's first have an intuition behind this Bayes theorem, right? So what this Bayes theorem is about, and how it's actually modifies the conditional probability. So let's go to the whiteboard and then have an intuition behind that, and then we will come back and then answer our question whether a patient will be diabetic or not, right, using the Bayes theorem. Okay, now let's come here and then see the intuition behind this Bayes theorem and how we use naive Bayes to actually take advantage of this Bayes theorem to make predictions. Okay, so let's take A, right, to be an event, right? Let's take A to be an event. So it could be any event, maybe an event that you go for meeting tomorrow, or the event that you travel tomorrow, or an event that it will rain tomorrow, or an event that you'll be going for glossary this evening, right? So it could be any event, right? Or an event that you roll a die and you get say 2 or 3, right? So it could be any event. And then if we take A prime, right, that is actually going to be an event that A will not happen. So if let's do it this way. So if we have A to be an event, then we can say that probability of A, right, will be P of A will be the probability of A, right, and then A prime will be that is not the A event, right, not A event. You can think of it that way. So if we have probability of A not, then it's actually going to be 1 minus the probability, right? The probability of A, right? So this is the probability of A happening, right? That's A happening. All right. And then this one will be the probability of A, right? A not happening. All right. So we have these two. We have these two probability of A happening and then the probability of A not happening. Okay, so now let's take, say, B, right? If we take B to be another event, right, B to be another event, okay, then we can have probability of B also, right? That is probability of B happening. And then if we take B not, right, that's not event, not B event, right, not B event. Okay, then we can also take probability of that, which is going to give us P. All right, we can take a probability of that, which is going to give us P of B naught, right? Which is just like 1 minus probability of B happening. Okay, so that's what we have over here. Now let's just take an example of just rolling a die, right? I think you're familiar with that, and that is actually going to make more sense. Okay, in this case, now if we say that the event A, right, is just just rolling a 1, right? So if we take a die, we're actually going to consider a die, right? So a die is having 1, 2, 3, 4, 5, and then 6, right? It's having 6 faces. So if A is rolling a 1, right? So the probability, right? The probability of A, that's the probability of rolling a 1, is actually going to give you 1 over 6. Okay. Then if we take, say, B, if we take B to be just rolling, if we take B to be, say, rolling an odd number, let's take that way, right? If we do it that way, then probability of B is actually going to give you we have 1, 2, 3, right, 3 odd numbers, so it's going to give you 3 out of the total 6. Okay, so this is basically like 1 over 2. All right, so this is what we have. Now let's bring in a condition here. So if we ask the question, what is the probability of A given B? Okay, initially we say that the probability of A is just rolling a 1. So what is the probability of getting 1 when you roll the die? What is the probability of getting 1? Which is 1 over 6. Okay, but what if we are given a condition that whatever we have on the die face is just odd number? Okay, whatever we have on the die face is just odd number, which means that we don't have even numbers. Okay, so now what we have here is this: we have 1, we have 3, we have 5, right? We don't have these. Now we don't have this. This is what we have. This is the new die that we have. So if we give that condition and we say that what is the probability of A given B, right? So what is the probability of getting 1 given that we have only odd numbers? Okay, now if we do that, right, we are going to get 1 out of 3, right? That is probability of getting rolling a 1 given 3 faces, right? So that's going to give you 1 out of 3, right? Just like we're having 6 faces, right? And then when we did probability of rolling 1, right, we'll have 1 over 6. So the same way, if we have 3 faces, probability of getting 1 is, out of the 3, it will be this 1 over 3. Okay, so it's basically like let me change this one. It's basically like you say that what is the probability of you traveling, right? What is the probability of you traveling? The probability that you will travel, given that it will rain tomorrow, right? Given that it will rain tomorrow. So basically that's how it is. All right. Now, having understand this, what we can actually do over here is to establish this in the form of a formula, right? So if we consider all of this, right, which includes A and B, right? If we consider all the 6 faces of the die, which includes A and B, so we can say that this probability, right, of all of the A and B, right, of that, right? If we consider that, right, of all A and B, we got 1 over 6, isn't it? Now, if we give that condition, right, if we are giving it a condition that we already have B, which has happened, right? If we already have B, which has happened, then it's actually going to, give us a new probability, right? Which gave us something like this, right? Which we ended up getting like this. So in this case, the probability, right? We're having this probability. So I'm going to write this one here, right? I'm going to write it over here, which is the probability. All right, which is the probability of A given B, right? The probability of A given B will be equal to this one. Okay, so that is the formula that we can get. So when we had all of them, when we had all the 6 faces, we're having 1 over 6, right? So we're having 1 over 6, and then when we give the condition that we only have all the numbers, remember the probability of B, right? The probability of B is nothing but this, right? Probably we got probability of B here, right? And we got it to be 1 over, 1/2 over here. So if you put it over there, you can see that this one here, 1, this one here, 3. So we end up having our 1/3, right? Which is the same thing that we have over here, okay? Which is the same thing that we have over here. So now we can actually establish this in the form of a formula in this way. Okay, so this is the conditional probability, right? This is the conditional probability that we have over here. Okay, now let's say that let me pick this one now. Let's say, all right, now let's say that we have independent events. So let me actually do it this way. Let's now consider an independent event, right? Let's consider this independent event. So let's say that these two, right? Let's say we have, instead of one die, right, let's say we have 2 dice, right? So we have dice A, right? So we have 2 dice, right? We have dice A, and then we have dice B. Okay, let's say we have two independent dice. So this dice A is having 6 faces, right? It's having 6 faces, 1, 2, 3, 4, 5, 6. It's having 6 faces, and this die is also having its own faces, which is 1, 2, 3, 4, right, 5, and then 6. Okay, it's also having its 6 faces. Now, what is actually going to happen over here is that if we say that if we give the same condition that we were doing earlier on, right? If we're doing the same thing now, if we pick die A, right? If we pick die A, and we want to have see the probability of rolling a 1, right? If we want to see a probability of rolling a 1, right? Considering die A, right? That's going to give you 1/6, isn't it? And if we pick die B, right? And we want to see the probability of say rolling a 1, right? It's also going to give us 1/6, right? It's just 2 different dice. So if we want to find the probability of rolling a 1 out of each of them, right, you're going to have 1/6, right? Now, this is what we have. What if we want to find probability of A and B? Okay, if we want to find probability of A and B, now we're going to have 1/6 multiplied by the 1/6, right? That's the 2 different dice, right? We're going to have it that way. Okay, we're going to have it that way, and this is actually going to give us 1/36. Okay, so we actually did it this way, like the probability of A, right? We just did probability of A. Okay, probability of A plus probability of B. Okay, that's what we just did. Multiply by. Okay, so you can see that this is probability of A times this. So we just multiply these two, probability of A multiplied by probability of B. Okay, that's what we just did over here. Now, having gotten this, right? Having gotten this, now let's let me actually make it a little bit bigger. Let's take it one more step, right? Let's take it one more step. Now, what if I say that what is the probability of A given B? In this case, if I say what is the probability of A, right, given B, that is the probability. Let's take probability of A to be the probability of getting a 1 when you roll die A, right, and the probability of getting 1 when you roll die B. Okay, so if I say what is the probability of getting a 1 from die A, right, given that die B has already been tossed, right? Now, there are 2 independent events, right? There are 2 independent events. That is, there are 2 different dice. So for me to get 1 on dice A has nothing to do with me getting anything on dice B, right? Whatever you will get from dice A has nothing to do with this one. Okay, so if I want to find that condition, and I say that what is the probability of A, right? The probability of A, right, given that B has already been tossed, right? This is still going to give me 1/6, right? It's still going to give me my 1/6. Okay, it's still going to give me my 1/6 because there are 2 different dice, and one has an event happening on one has nothing to do with an event happening on the other. In the same way, if I want to find probability of say B given A, right? Probability of B given A is still going to give me 1/6. Okay, it's still going to give me 1/6. So the 2 of them has nothing to do with the other. All right, and then this one is nothing but this, right? If you want to intuitively come up with this, you can actually see that probability of A given B, right? We say that it's 1 over 6, right? So now this one is more like this, right? It's just the same thing as this. Probability of A and B, okay, divided by the probability of B, right? So it's just the same thing. That's the probability of A given that B has already happened, all right? And it's still going to give you the same thing if you want to move further. You can see that probability of A and B, remember that we got probability of A and B is nothing but this probability of A multiplied by probability of B. So if we say that probability of A and B and we replace probability of A and B with the probability of A, right? Probability of A multiplied by the probability of B, right? If we do that, right? And then now we have divided by our probability of B, right? We have it this way. Now you see that this one, right? This one can cancel this one out. All right, now you can actually see that we have only probability of A left. All right, you can see that we have only probability of A left. And that's why over here you see that probability of A, given that B is still 1 over 6, is still the same thing as probability of A. Okay, and if you want to find probability of B given A, it's still the same thing as 1 over 6. That is the same thing as probability of B. Okay, because if the two events are independent and they don't actually depend on any of them, right? So the probability of something happening on one has nothing to do with the probability that this will happen. I mean, an event will happen on the other. Okay, so this is another way of expressing independent event, right? This is another way of expressing independent event. So it's basically this one, right? This one here. This I can actually bring this one here because it's just equal, right? So let me just write it here. That is probability of A, given that B has already happened, right? It's equal to this. And basically it's equal to, right? It's just the same thing as what we did, right? Probability of A and B, right? Which is equal to the probability of A and then the probability of B. Okay, so this one is one way of expressing independent event, and this is another way of expressing independent event. Okay, so both of them works fine when you want to consider an independent event. Okay, both of them works fine. Okay, so now let's actually take it one more step and see where the naive Bayes actually comes in, right? Let's see where the naive Bayes actually comes in. Now let me pick this equation, right? I'm going to just pick this same equation over here, right? I'm going to pick this same equation and then bring it down. Okay, I'm just going to bring the same thing down. So let me actually make it blue here, right? So I'm going to bring this whole equation here, right? I'm going to take it all the way down, right? So let's go there and then write it. So we have probability of A, given that B has already happened, to be equal to the probability of A, right? And okay, it's equal to the probability of A and B, right, divided by the probability of B, right, divided by the probability of B. Okay, so this is basically what we have. Okay, and I mean, if you have y equals x, right? If you have y equals x, it's the same thing as writing x equals y. Okay, it's the same thing. So with this equation, I can still write it this way. I can just write this part first, right? So probability of A, right? Probability of A and B, right? Divided by the probability of B, right? It's still equal to, then now I'll bring this part here, right? Is equal to the probability of A given B, right? It's the same thing. I mean, it's the same thing over here. Okay, so now I can write it this way. Let's say we multiply each side by the probability of the probability of B, right? Let's say we do that, right? Then this part 2, right, by the probability of B. Okay, so this part, this one is going to cancel that. Then I'm going to get the probability of A, right, and the B over here, right, to be equal to, okay, to be equal to the probability of A, given that B has already happened, multiply by the probability of B. Okay, multiply by the probability of B. All right, so this is basically what I will get over here. Right, this is what I will get over here. Now, as I said, if we have say if we have A plus B, right, it's the same thing as writing B plus A. Okay, it's the same thing. So if you're saying A, right, if you're saying A and B, right, A and B, right, A and B is the same thing as writing B and A. Okay, it's just the same thing. So I'm going to just switch the letters inside here. So probability of A and B can also be written as probability of B, right, probability of B and A, right. We can also write it that way, right. And when we do that, right, just like we are switching the letters, okay. So when we come here, instead of this probability of A and B, I can write it this way, probability of B, given that A has happened. So I'm just switching the letters inside there, okay. Multiply by the probability of A, right. So I'm just switching the letters inside there. All right. So we can also write it in this way, right. We can also write it in this way. Now, we are saying that this part, right, let me pick this. Okay, what we're saying is that this one, that's probability of A and B, is the same as probability of B and A. Okay, they are all the same thing. Probability of A and B is the same thing as probability of B and then A. Okay, they are all the same. Okay, so if they are the same, right, if they are same, if probability of A and B and probability of B and A are the same, which means that this part is also the same, right? We can also equate both of the other sides, right? We can equate both of the other sides. So I'm going to write this part, right? I'm going to bring this part, which is this one. Let me actually do this. Okay, I'm going to bring this part, which is probability of A given B multiplied by the probability of B. I'm going to bring it down all the way down. So let me go a little bit down and then write it. So that was probability. So that was probability of A given B, right? Probability of A given B, right? Multiplied by the probability of B. Okay, multiplied by the probability of B. All right. So we are saying that this is equal to this one. This is equal to this one. Okay, we're saying that either side of the equation is the same. So I'm going to bring this one 2 down here. Okay, I'm going to bring this one 2 down here. So that is actually going to give us this probability of B given A, right, multiplied by the probability of A. Okay, multiplied by the probability of A. All right, so we can actually equate the other side also. All right, now let me try and then bring this one. So let me instead of writing it this way, what I'm going to do is to actually divide each side by the probability of B, right? Because I want to get rid of this probability of B. So I'm going to divide each side by that, which is probability of B. All right, I'm going to do that. So over here, this one will cancel this one out. Okay, so if I do that, right? Okay, if I do that, now what is left is this, right? Now I'm left with this. I'm left with the probability of A given B. Okay, I'm left with this one on this side. And then I'm having this probability of B given A, right? I have this multiplied by the probability of A. Okay, multiplied by the probability of A divided by this, which is the probability of B. Okay, so now this is what I have. All right, this is what I have, and this is what we refer to as the Bayes theorem. Okay, this is what we refer to as the Bayes theorem, and this is what the naive Bayes is based on. Okay, so you can call this part, right? You can call this. So let me just write it over here. So this is what we refer to as the Bayes theorem, right? It's nothing but the Bayes theorem. Okay. Is the Bayes theorem, and this is what the naive Bayes is basically based on. Okay, so what we say is that this is the probability that we have. This is the prior probability. This is the probability that we know already, and this is what we want to find, right? Given the new information, this is what we want to arrive at. So this becomes the posterior, Right? This becomes the posterior probability. Okay, so the probability, right, over here, the probability of A, given that B has happened, right, equals the probability of B given A, right, multiplied by the probability of A divided by the probability of B. Okay, so basically this is what the Bayes theorem is all about, and this is what the naive Bayes is actually based on. Okay, this is what we are saying is that if I should give you an example of our earlier discussion, so we were saying that what is the probability of you going for meeting, right? Going for meeting. So probability of you going for meeting, given that there will be a heavy rainfall, right? There will be a heavy rain at the next day, right? So this one is actually going to be expressed as what, as the probability that is actually, the probability that you go for the meeting, given that there will be a heavy rainfall, right? You can think about it, right? It's actually going to be the probability that it will rain, right? So if it doesn't rain, then you go, right? So what we want to do finally is to go for the meeting, right? But if it rains, that is another information, right? So we have to first think about the probability that it will rain, right? Then, given the fact that I want to go for the meeting, okay? So this is actually meeting, right? Given the fact that I want to go for the meeting, okay? So this is what we have at hand, right? That we want to see the probability that it will rain. If it rains, then it's actually going to affect the fact that I will go for the meeting, right? It's going to affect the posterior that I want to arrive at, right? Multiply by the probability that I will even go to the meeting in the first place, right? Multiply by the probability that I will even go for the meeting, right? Multiply by that probability. All right, divided by the probability that it will rain. So the it will rain is the condition that we are considering over here. Okay, so the probability that it will rain is the main condition that we are talking about here. All right, so we have this. So this is the information that we have, right? The probability that it will rain, right? This is the this is the information that we have, which is actually the prior, right? Which is the prior. Right, the information that we have already. And then this is what we want to arrive at, which is actually going to be the posterior. Okay, the probability that I'll go for the meeting given the fact that it will rain. All right, so this is basically what the Bayes theorem is, and this is what the naive Bayes is based on. Okay, so from here we will actually move on to the lab session, and then see how we are going to see how we are going to implement this Bayes theorem. Okay, it's actually called naive Bayes due to the fact that it makes assumptions of some independent event, right? It takes assumptions of some independent event. Okay, so basically that is a disadvantage to the Bayes theorem, taking the fact that it's making assumption that the two events are independent of each other. Okay, and one application of this Bayes theorem is when you want to classify an email as spam or not spam. Okay, so what basically Google will do is that it will define certain words, right? Certain words, maybe win, right? Maybe win, some words, right? It will first define some words, maybe win, maybe some words like lottery, right? Something like that, or maybe something like spin and win. Some words which are actually like spammy words, right? Spin and win, right? Okay, some words. So they will first define some bag of words. Okay, so what is happening is that what Google will say that with this email, right? Whether the email is actually going to go into the inbox, right? To the inbox, right? Or it's going to go into the spam folder. Okay. So what they will do is that they will define certain words already. They have some bag of words already. So if the new email is coming in, right? If the probability of the new mail coming in, right? If someone has sent you an email, right? What is the probability of this email going into the inbox, given that there are certain words, right? So if these words are present, right? If these words are present, then it should go to the inbox. The spam folder. If these words are present, it should go to the spam folder. If they are not present, then it should go to the inbox. Okay, so given these words, right? Given these words, what is the probability that the email coming in will land into the inbox or will land into the spam folder? Okay, so basically they base on this Bayes theorem to actually make that classification over there. whether a email will land into your inbox or not, right? They based on this Bayes theorem to actually do that. All right, we will see more of this as we progress in the course. Okay, so let's proceed to the lab session and see how we are actually going to use this Bayes theorem to make to build a classification algorithm. Okay, so see you in the lab session.